In another video, we looked at something called differential equations, which are equations that simply have derivatives in them. In this video, we're going to look at a particular kind of differential equations called separable differential equations and how we might solve this type of equation. A separable differential equation is an equation in this form where we have the derivative equal to some function of y times some function of x. It doesn't matter if this function of y has a quotient in it or not. It does look like here it would just be a product, but it can have a lot of different forms. But the idea here then is that we could solve this derivative we could solve this differential equation by getting everything involved with y on one side of the equal sign and everything involved with x on the other, and then we could take an equation like this and integrate both sides, and then we end up with a solution, a general solution to the differential equation. At that point, we would be able to take some initial conditions and get a particular solution for that differential equation. So here are a few differential equations. We looked at a few of these in the previous video on differential equations. This first one here, what I've done is I divided both sides by y to get 1 over y over here on the left side, and I multiplied both sides by dx, and we get the equation 1 over y dy equals x plus 1 times dx. Since this is a function of y times a differential y, and that's equal to a function of x times the differential of x, then this is what's called a separable differential equation. In the second one here, if we multiply both sides by dx, we get this equation here, and we run into a problem with this one because there's no way to get y on the other side with the dy, since the y is being multiplied by the differential of x. So this one is not a separable differential equation. This next one here, we can get all the y's on the left side and all the x's, which there actually aren't any besides the differential of x, on the right side, and so that is a separable differential equation. This last one doesn't immediately look like it's a separable equation, but since we can write that as x squared times y squared, then we can divide by y squared on both sides, and what we end up with a separable equation there. We'll take this last example with an initial condition, and we'll look at how we can actually go forward with solving such an equation. So what we have here is not only a differential equation, which is separable, we saw that on the last slide, but we also have an initial condition. We know that when x equals 1, y is also going to equal 1, and we'll be able to use that initial condition to get a particular solution to our differential equation. So we'll start here by separating variables, and to do that we'll have to distribute, in a sense, the square, and so we get 1 over y squared dy equals x squared dx, and then for the purposes of integrating, we're going to go ahead and rewrite this 1 over y squared as y to the negative 2, and at this point we can just integrate both sides. Now, on the left side, we're going to integrate with respect to y, since we have the differential of y there, and on the right side, we will integrate with respect to x, since we have the differential of x there. Now, these are both indefinite integrals, so we're going to have a constant of integration involved. On both sides, we'll have a constant of integration, but we only need one. We'll look at this here. So if we integrate the y to the negative 2, we increase the power by 1 and divide by negative 1, so we get negative y to the negative 1, and then we have x squared, increase the power by 1 and divide by that power, so x cubed over 3. And if we added a constant here and a constant here, but then subtracted this one from this one, we're going to only end up with one constant. So we don't need a constant on both sides. We still do need one constant of integration, though. To figure out what c is going to equal, we'll go back up to the initial condition, this y of 1 is equal to 1, and plug that in, and we get c is equal to negative 4/3. This solution right here is called a general solution, and to get the particular solution, we're going to use this constant then, and plug that back in, and then we'll want to simplify. If we can, we'd like to get y by itself, so it is an explicitly defined function rather than an implicit function. So we'll start by changing that to a positive 1 over y, we can combine those fractions there and then take the reciprocal of both sides to get this particular solution.